We discussed the derivation of an equation to calculate the deformation of axially loaded bars in a previous video, and that was delta, the deformation, is equal to PL over AE or FL over AE, where F is the applied force and length of specimen is L, A is the area, and E the Young's modulus of the material. Now let's see the application of this equation in this video. What you have here is a member, a body here applied by two forces at the ends, and also another force in this direction. So what you have here is 100 kilonewton acting at point 1, 200 kilonewton acting, let's say 2, 3 and 4, 200 kilonewton acting here to the left, 250 kilonewton acting to the right, and then 50 kilonewton acting to the right. So these are all forces in kilonewton, and the length of the specimen is given as 2 meter, 1 meter and 1.5 meter. So let's see if we can calculate the deflection of this member which is acted upon by this force system. Now this system under the action of these loads are in equilibrium, or this force, the member is in equilibrium. So let's consider each member individually and then we can form an equation. So what you have here is the first member. So you have because the system is in equilibrium, if you just consider this member, this should be in equilibrium, which means you have 100 kilonewton here, and that is made equilibrium by the application of same 100 kilonewton at the other end, and therefore the deflection of this member will be caused by this applied load. Now if you move on to the next segment, you have again this is totally in equilibrium. Because the entire system is in equilibrium, these two segments should be in equilibrium, and you have 100 kilonewton acting at this point which is already known, and you also have a 250 kilonewton acting in the opposite direction. So in order to make this system equilibrium, you will need to have 150 kilonewton acting towards right. Now if you move on with the same analogy, then you have the third, we consider the system up to here. Now you have 100 kilonewton non-load acting here, 250 kilonewton acting here, and you have 200 kilonewton acting to the left, that is here. So the net force is 200, 100, so 300 to the left, 250 to the right, so you will need another 50 to the right. So that is the distribution of the forces. Now the area, let's consider the area of members is for the first one, let's consider this 1000 millimeter square, and let's consider 2000 millimeter square for this one, and again 1000 millimeter square for the third portion. And let's consider rigidity or Young's modulus of steel, which is usually 200 gigapascal. So let's take E is equal to 200 GPa, and therefore you have applied force P 100 kilonewton here, so that will give you according to this equation, you will have PL over AE. That will give you 100 kilonewton, 100 into 10 raised to 3 times length, that is 2 meter. So PL over A, that is 1000 millimeter square. Let's transfer the meter to the millimeter, so that's 2000, and area is 1000 times 200 gigapascal, so that's 200 times, actually it is times 3 to convert to Pascal, but because we are using millimeter here, we can take it in kilopascal, so that's 10 raised to 3. You should be using that is 200 into 10 raised to 9 Pascal. However, because it's Newton per meter squared, and we are considering millimeter squared here, I have only taken the 10 raised to 3 to take into account of the meter and the millimeter. So this will be the deformation of the first member, and for the second one you have the net force of 150 acting towards right and left in this member. Because this 250 you cancel 100, so what you left with is 150, and the 150 is compressing from the other end, so the deformation will be negative because it's a compressive force. So what you have is minus 150 times 10 raised to 3, and the length is 1 meter, so that's 1000 millimeter over area is 2000 millimeter square, and the same Young's modulus, that is 200 into 10 raised to 3. And for the third member, what you have is 250 acting, 50 acting in this direction, and 50 acting in this direction. So that will be a pulling load of 50 kilonewton, and therefore that will be a positive elongation, or it's an elongation rather than a compression. So you have 50 times 10 raised to 3 times length is, I think that's 1 meter, or yeah, that is 1.5 meter. So you have 1500 millimeter over area is, I believe it's 1000, yeah, that is 1000 millimeter square. So you have 1000 times 200 times 10 raised to 3. So calculating these figures, you will get, this will give you 10 raised to 3 cancels, 200 cancels 2000, you have 10 here, so 1, that will give you 1 millimeter, and here you have 200,005, and that will give you, calculating, that will give you 3.375, so that's 0.375, and on the third case that will give you 200, this is 1500 over 4000, that will again will give you 0.375. so your net deflection will be, this is the diagram for the axial load. In the first member you have 100 kilonewton as we discussed here. The second member you have 150 kilonewton, and in the third member you have 50 kilonewton. So you have 100, that is plus 100 kilonewton, and in the second one you have minus 150 because it's a compressive force, and in the third one you have plus 50 kilonewton. This is the axial force diagram for the system. So you have 100 minus 150 and 50 kilonewton. Now for the strains, you have 1 millimeter strain here, or we haven't calculated the strain. The deformation, the axial displacement is for the first member up to 1000 millimeter, I believe. No, it's 2 meter, so that's 2000 millimeter. You have an axial displacement of 1 millimeter, and then the net displacement here is 0.625, because you have a reduction of 0.375, that is negative displacement, and therefore at this state the net displacement will be 0.625, and then you have another positive 0.375, therefore the net deflection at the other end will be 1 millimeter, and the total deflection will be 1 millimeter plus minus 0.375 plus this is plus 1 plus 0.375, which will give you 1 millimeter. That will be the net deflection. This minus 0.375 is the compression of the second member due to the applied load of 150 kilonewton. So that's negative load, and your strains will be you will need to calculate the strains for each cases. So we have calculated the deflection using this equation in this program. Just to explain once again, you have 3 members in this body, which is acted upon by 100 kilonewton here, 250 towards the right, 200 towards the left, and 50 kilonewton towards the right. So considering each member, because the entire system is in equilibrium, each member should be in equilibrium. So you get 100 kilonewton tensile force on the first member, and 150 kilonewton compressive force on the second member, and 50 kilonewton tensile force on the third member. First and third member will have an expansion or an elongation, whereas the second member will have a compression. So the net deflection, net deformation will be 1 millimeter for the first member, minus 0.375 for the second member, and plus 0.375 for the third member. Therefore the net deformation will be 1 plus minus 0.375 plus 0.375, that is equal to 1 millimeter, the total net deformation, axial deformation. Once again, thanks for watching. Keep watching for more videos. Thank you.